But in today's lecture, actually the end of today's lecture is where we're going to show relationship between two-point correlator and the Green's function of the differential equation that is associated with, say, the wave equation, which gives you the saddle point solution. Right? So we'll see that. Yeah. So let me start. Okay. So what are we going to do today? Today we're going to do a coherent state path integrals. And this will give us a tool. It's not the only way, but it's a very useful way to do quantum field theory. So just to give you context, up to now we described classical field theories. We discussed classical field theories using Lagrangians. Okay. Then we quantize their corresponding Hamiltonians. Okay. So we had, yeah, we could say that we had one example would be the Klein-Gordon theory, d mu phi star, d mu phi minus m phi squared. And then we move to a Hamiltonian, which is something like pi squared, maybe I'll write it like this, pi squared plus phi squared plus m phi squared. This is h. This is the Hamiltonian density. And from this, we then diagonalize it using ladder operators. So eventually we can write this as some h bar, let's say h bar omega k, a dagger k, a k, and plus the infinity term. So this, and these are ladder operators, which creates particles. And this is, this is enough. This is basically a quantum field theory. We describe it, so we can add, we can add to the Hamiltonian. We can write now something like, h bar, omega k, a dagger k, a k, plus then we can add maybe some interaction. I don't know, something like a sum over p and q. I don't know, some u, q, a dagger p plus q, a dagger k minus q, a k, a p. I don't know, something like this, and that would be that would describe a term that already breaks the integrability and the quadratic properties of the Hamiltonian, but we can take this into account and study it, and we can add different terms which have different meanings. We can couple these kind of particles. We said we're calling these guys particles. We can couple them to other fields and do all sorts of stuff. But it turns out that it's extremely useful to reformulate this quantum field theory in terms of a Lagrangian and a path integral formalism. It's kind of equivalent to, say, initially you learned about Hamiltonians, you solve wave functions and all that, and then later you learned about Feynman path integrals. Feynman path integrals are different, right? When you do a Feynman path integral, you're not treating some Hamiltonian as an operator. Instead, you're taking some classical action, but you're summing over it in a clever way that takes into account quantum effects. And it turns out that many things, let me give you examples, like renormalization theory or perturbation theory and stuff like that, are more difficult to do in this operator formalism. So instead, we want to use actions. We want to enjoy, what Feynman path integral formalism has to do. And in fact, the Feynman path integral is most, what makes it really, its biggest contribution to science or something, shows itself in quantum field theory. Okay, so we really want to find a way to formulate, this kind of what I would call a many-body description or a quantum field theory in terms of path integrals. And that's the idea. Now we have, these are like particles. Okay, they're the well-behaved object that we want to look at. Now we want to write general theories like this in terms of path integrals. So that's what we want to do. And another thing I want to mention is that we basically looked at two paradigmatic theories. One of them was, this Klein-Gordon theory, but the other one was the Dirac theory. So, this was like, let's put this Klein-Gordon. Okay, and we had Dirac theory. So for Dirac theory, we could write something like L is equal to psi bar, I gamma, let's write it like this. Gamma mu d mu psi minus m psi squared. Okay, and what these two theories describe, basically, they're like paradigmatic examples. This one is a bosonic theory, and this one is a fermionic theory. So we saw that in order to stabilize a vacuum here, we need to use fermions. And these will actually be enough. These are paradigmatic examples of quadratic theories, free theories. The particles in these theories are free. Okay, that's because we diagonalize them with waves. They propagate forever. Nothing stops that. That's what we call also integrable theories. Very, very simple. Simplest possible thing. But any theory we want to consider, these will be like the cornerstones. So we can, for example, add interactions on non-analyticities here, in quartic terms here, or we could add interactions here. You could think about the general structure here as some sort of matrix. So this kind of structure might be more complicated, like in a lattice, but still it's just going to be, some spinors with a matrix that connects them, and that's what we also have, say, in a crystal or many other well-known examples. So these are our paradigmatic free theory. Okay, so it turns out that the way to move from this to a path integral is, and in both cases, this is what we're going to have. We diagonalize this Lagrangian, or sorry, not Lagrangian. Here we go to Hamiltonian, right? We have Hamiltonian, which, and okay, maybe I'll write it. What was the Hamiltonian here? It was, I guess, we have I, psi dagger, okay, sorry, gamma goes, it's really hot in here, plus m, oh, sorry, let's write psi bar, and then we have psi bar psi. This is our Hamiltonian. Oh, and also here, this is not psi like that. It's psi bar psi. Okay? So this is our Hamiltonian. This is actually what we... and these psis, by the way, they take the same role as these. So, sorry, maybe I should mention it again. This we can then diagonalize, right? And we had a theory. Yeah, so maybe. So this would be like a bosonic theory. But then we can write a general fermionic theory as, what did we have? We had some, H bar. Let's not write H bar. Let's just call it, we had something like EP, A dagger, P, alpha. There was an alpha here. A, P alpha, plus B dagger, P alpha, BP alpha, right? Something like this. And then to this theory, okay, we can also add interaction terms. We can have something like, I don't know, like some G, I don't know, A dagger, P alpha, A, P dagger, beta. This can be, sorry, here we need a sum again over, say, P and Q. This can be a function of Q. And then we have again, I don't know, P plus Q alpha, K minus Q beta, A, K beta, A, P alpha. This is, say, interaction only within the same particle A, and density like interaction, but we can add many terms like that. You can play around with it, and the idea is that we want to treat these kind of models. So it turns out that the way to write a path integral for these kind of theories is to use coherent states. So what we need to discuss or refresh your memory about coherent states, and refresh my own memory because today was extremely hectic, so I barely remember myself what coherent states are. So the idea behind a coherent state is that they're eigenstates of these ladder operators. So generally, if I have, and let's start from bosonic ones, bosonic coherent states. So the idea is that if I have a coherent state phi, it gives me phi times the state phi. That's how we define a coherent state. And we can generate a coherent state like this by taking e to the phi a dagger times on the vacuum, which would be a sum over n equal to 0 to infinity of phi a dagger to the power of n over n factorial acting on the vacuum. So you see that this coherent state is a superposition of many, many different occupational states. And then, okay, and I'll also add to your exercise on the Dirac maybe a few exercises on these coherent states, and you can play around with them and show, explicitly by applying, A on this, that this holds. All you really need is the can be shown using the fact that a dagger to the power of n is like n a dagger to the power of n minus 1 plus a dagger to the power of n a. And the point is that the second term, because it's acting on the vacuum, destroys it. So you can show it using that. It's kind of trivial. And then this implies, on the other hand, that you know, by Hermitian conjugation, we find that this is true. Right? And we can also work out then that because of the commutation relation between these A and A dagger acting on phi is like a derivative. Okay, so this is d to d phi in the space of these phis. Okay, let's see what else do we have. And now we can also work out overlap of two coherent states. So if we compute, say, phi 1, phi 2, like this, we get e to the phi 1 star phi 2, and therefore phi is equal to e to the phi squared. Okay? What does this imply? Well, you can see from here, basically, that each one of these coherent states actually includes all excitations in the Hilbert space. So we should expect these states to be able to span the entire Hilbert space. Okay, there's the same, you have that you can count, you have more than enough states. But on the other hand, you can see that they're not orthogonal. So this implies that they are what we call an overcomplete basis. Okay, they span too much, there are too much of them. So then if we want to define the identity matrix in this space, we need to use what is known as the resolution of identity, which, when you have a complete basis, the identity is trivial. It's just an outer product sum over all states. Here, let's start from the fact that these phi's are continuous parameters. We have an infinite number of them. And yeah, as I mentioned, they're not orthogonal to each other. That also goes hand in hand, right? We couldn't have an infinite number of them, which is, say, for a complete basis, we would have, in this case, a discrete set, an infinite discrete set of states. Here we have an infinite continuous state, so it's a different strength of infinity. So obviously that also implies immediately that they must be overcomplete. And then we define the following thing: an integral of d phi star d phi. Here we're treating phi star and phi as two orthogonal, like you could think about this like a two-dimensional integral, like dx dy, or you could look at phi and phi star at e to the minus phi squared phi. This is an operator, okay, and this is the identity. So how do you show that it's an identity? You want to show that it gives you it doesn't modify a state. Okay. In this space. So just, you know, if you want to prove that this, what you want to show is that M, so you take, so you can span the entire Hilbert space using these different excitation number states, and you want to show that this is delta n m. Okay, and the way to do that is so you have something like the integral d phi star over pi e to the minus phi squared, and then we have m phi n. Then we have two things we need to explain. The first one is that phi n, this overlap is phi to the n divided by square root of n factorial delta. No, there is no delta. Right? Okay? And then that's one thing we need. And so this integral becomes an integral dx dy over pi e to the minus x squared minus y squared, so it's like a Gaussian. And then these two guys, they become, so this guy becomes x plus iy, this becomes x minus iy to the power of m, and this guy becomes x plus iy to the power of n. And yeah, I guess you can think about this as how does it work? These are like vortices or something. It's the opposite of poles. These are zeros, but by symmetry they cancel out unless m is equal to n. Okay, and then you get I forgot, this is like square root of m. This is square root of n. And then you just get the nth moment of this Gaussian distribution, which is exactly n factorial, and then you get delta n. So that gives you the resolution of identity. And then finally we can generalize phi to be a vector phi, which is like, you know, phi 1, phi 2, phi 3. And these phi's, they can be, you know, like a spatial coordinate, for example. So let's imagine that, if you remember, well, I know you don't remember because it's a different course and I'm mixing up things. But here, for example, you have these a of k. K is a continuous parameter. So we might, for the purpose of, you know, getting our heads wrapped around it, we might discretize k, and then we have a discrete set of vectors you know, this is the first k, this is the second k, this is the third k, and in the end we can take, you know, the number of these k's or the distance between them to 0. But for the purpose of the calculation, you can imagine that phi is like a vector with different, and these are, say, labeled by k. Yeah.
It's like in Dirac's equation, right? That you have spin and negative energy indexes, but
you can, Well, what I'm trying to say is that up to now we discussed a single coherent state. Like we had a single harmonic oscillator, but we know that in a quantum field theory we have a continuum of these. That's how we think about these quantum field theories. It's like, at least when they're free, the free quantum field theories are like a continuum where at each point in space you have a harmonic oscillator. Okay, for each dimension, for each orbital, for each spatial dimension, so on and so forth. And well, actually, for each spatial dimension, it depends on what we're looking at. But that's kind of the point. So I just want to say that let's assume that we're discretizing. And the reason I'm saying that is because I want to describe now phi as a vector, okay? Or I could equivalently write something like phi of k. K is just a generic index, or then I would have something like e to the sum over k, phi k, a dagger k, acting on the vacuum. And then if I do something like, phi vector, okay, then that would be e to the sum over k, phi k star, phi k, and the resolution of identity would be something like, there would be something like a measure. Okay, maybe I'll write phi dagger like that. Then I have e to the minus phi dagger phi. Phi, and this measure guy, for bosons, it's like a product over all these k's of d phi star k, d phi k over pi. So now we can use this to compute expectation values. So when we look at Hamiltonians like that, we want to take their expectation values. And here we're going to specifically focus on expectation values of, as Joseph mentioned once, normal ordered Hamiltonians. It means that I'm going to assume that everything, like I took all the A's to the right and all the A daggers to the left. And we can do this either by commuting the Hamiltonian, but we saw that also physically it makes sense to assume that any physical theory comes normal order. So say our Hamiltonian has this form. Let's look at the top Hamiltonian. So the Hamiltonian itself, H, of the Klein, this is not some bosonic field theory, would be, say, an integral d3 p over 2 pi cubed h bar omega p a dagger p a p, and then we have plus another d3p, d3k, let's call it d3k, d3q over 2 pi to the 6, and then we have something like, I wrote there a uq, and then I have a dagger p plus q, a dagger k minus q, a k a p. Okay, this is like a generic Hamiltonian. By the way, do you understand why I write these momenta? Did you ever see these kind of balance between the momenta? Like, for example, why is this U of Q and not P or K? What's going on here? Like, do you understand, or did you ever see anything like that? I know that you guys probably have.
What is U?
U is the interaction in this case. So we have a quadratic term, which describes the free part of the theory, which we discussed in the previous lectures. Okay, this is the case for bosons. So you could think about it like Klein-Gordon theory. But now I allow these particles to interact. Okay, if you want, you could think of the Klein-Gordon theory as phonon theory, right? If you remember when I talked about it, I said you could think of it like optical phonons, for example, in a crystal. And then you could add to the optical phonons, like especially longitudinal optical phonons, by the way, you could add anharmonic terms. You know that anharmonic terms, they go like the displacement to the fourth, right? The quadratic, the harmonic part, which describes, you know, a harmonic theory of crystals is quadratic, but the anharmonic part would be, so you could have also cubed terms. I'm putting that aside for a moment, but let's say you have quartic terms. They go like U to the fourth, and then you get terms like this. This describes interaction between phonons. Like you have two phonons which are destroyed and two phonons that are created. So this diagram, you know, diagrammatically, which we will see, it's like two phonons are coming in, you know, there's a scattering event, and then two phonons come out. And then what I'm telling you is that the amplitude of this process is UQ. And you see there's a sum over all P, all K, and all Q. And I chose the incoming are like with a momenta K and P. And the outgoing are coming out with P plus Q and K minus Q. And I'm asking you why. Why did I choose to label them in this way? Did you ever see this notation or this choice of momenta? Any answers? Or?
The exchange momenta. That's where you can write the conservation of momentum.
Right. This is in fact a generic form of an interaction which only depends on the difference in real space between the two coordinates. So Q is what we call the momentum exchange, and this form ensures that we have a spatially invariant theory. It doesn't depend on where you are. Okay, so that's why the interaction only depends on Q. Q is the exchange momentum which couples to the difference between the two. So if this U in real space, let's write it like this. If U, which depends on the coordinates of these two particles, is U of R minus R prime, then you can make a Fourier transform with a single coordinate, and that coordinate I call it Q. That's the momentum exchange. And at home, you can convince yourself by starting from a real space interaction like this, and having a term that looks like U of R minus R prime times a dagger of R, a dagger of R prime, a of R prime, a of R, which is basically like a local interaction of particle-particle interaction locally, and you can Fourier transform this and you will get this form. It really is extremely hot. Okay? You turned on the AC, right?
Maybe we can open the windows.
Yeah, I'll do that. Try to do that. The only problem with that is that it brings in a lot of noise. Open this to get some air. smoothie. Okay. Good. So now, how do I take an expectation value like this? The beauty of it is that you see, because it's normal ordered, right? Because it's normal ordered, then I can compute, I can say, I can look at something like phi h phi, but remember that phi is not phi has a weight to itself, which we don't want, so we divide by phi, and this gives us our Hamiltonian, and this will just be an integral, in our case, d3p over 2 pi cubed, and then I have h bar omega p, and then I have phi, right, phi of p star phi of p plus integral d3k d3q divided by 2 pi to the 6 uq phi phi star of p plus q, phi star k minus q, phi k, phi p. Okay? And now we're getting a taste for how these kind of theories are represented in, and what we can denote this, okay, for future use as h of phi star and phi, or phi dagger. Okay, so whenever I write something like this, I mean take your Hamiltonian, assuming it's normal order, okay, and just substitute everywhere where you have a dagger with phi star, and everywhere where you have a phi. Now let's define the trace operation. Trace. So if I want to take a trace of an operator, trace of some generic operator, then by definition this thing is a sum over n. O, so O is some generic quantum operator, and I want to compute its trace. You'll see in a moment why. Okay, and n is some complete basis. Your how do you write favorite? Is there an I here?
Favorite.
What?
Favorite.
Favorite complete basis. Okay? Whatever, it can be any complete basis. Then what we do is we stick here and here resolutions of identity. Okay? But preferably, a very nice complete basis is, of course, when these are the Fock states, the occupation states. Then we get an integral, we have a sum over n, an integral d phi dagger phi. Okay, maybe I'll continue this for the time being here because I'm tired of switching chords. e to the minus phi dagger phi. Okay, so I can either write the sum over k explicitly or just assume it stays as a vector product. Remember that anytime a vector product is actually a sum over whatever, k, spin, orbital, okay? And then we have n phi o n. And then we can switch, because these are C numbers, they can just move them, shift them around. And I get an integral d phi dagger phi e to the minus phi dagger dot phi phi O sum over n phi. Okay. Now this guy is not a resolution of identity; it's just identity. It's a trivial resolution of identity. So then we're left with integral d phi dagger phi e to the minus phi squared phi o phi. So this is a trace. So this is equivalent to that. Now we're in position to compute the path integral. No, before I do path integral, okay, I do fermions. Okay, questions about all this? How am I with time? What's the time? So let's do fermions and then go on a break. Okay? Sounds reasonable?
Sounds reasonable.
Okay, now, so this was all bosonic coherent states. What happens with fermions? So with fermions, as you probably already know, we have a problem because, say I want to describe, okay, fermionic coherent states. Say I want to have a fermionic operator, say C, or maybe we can call it psi, acting on some eta, giving me eta. And that's what I want. Now let's imagine that I have, like over there, where I had a space of many of these oscillators. Say, I have two positions in space, right? So I want to have like a vector with two positions. So I want to have something like psi 1, psi 2, acting on eta 1, eta 2. And this will give me, say, eta 1, eta 2, eta 1, eta 2. But on the other hand, this guy is also equal to minus psi 2, psi 1, eta 1, eta 2, which is equal to, say, minus eta 2, eta 1, eta 1, eta 2. Okay? So in order for all this to work, we need eta 1, eta 2 to be equal to minus eta 2, eta 1. Okay? So that implies that, again, just like in Dirac theory and Clifford algebra, we need basically these numbers to obey the Clifford algebra. So the question is, well, actually, that's not true. I take that back. It's not exactly Clifford algebra, because when you square them, you don't get the identity. So we need numbers that anti-commute, and that's what they call Grassmann variables. Okay, so then we need to say a few words about Grassmann variables. So to the best of my understanding, and I haven't checked carefully, Grassmann developed this formalism, somewhere in the middle of the 19th century, so well before all quantum field theory and Dirac equation and quantum mechanics, just as a mathematician, then became very important for this purpose. So the first thing is find my hands and legs. Okay, so we want okay, so we want eta 1, eta 2 to be equal to 0, which implies that eta squared for all, eta j squared is 0. Okay? So 2 Grassmann variables squared are 0. Then there are a bunch of definitions. So differentiation says that d eta j to d eta I is equal to delta ij, which is just what we're used to. But the integration is weird. So integration gives us an integral d eta I. And this integral here, I'm talking about integrating over the space of these variables. So you could think about an integral of a number from minus infinity to infinity. Here it's an integral over the space of these variables. Then this guy is basically 0. Okay, but the integral d eta I times eta I is 1. Okay, and then that implies, for example, that the integral over d eta of f of some eta, okay, some function of Grassmann variables, is actually the integral d eta of, say, f of 0 plus f tag of 0 eta plus 1/2 f double prime of 0 times eta squared plus 1/3 f 3 of 0 is eta times eta cube plus ta 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 ta. And when you do an expansion like that, first of all these are trivially 0. Okay, all these are trivially 0 because of this rule here. And then this guy is also 0, so we just get f prime of 0. Okay? Which is the f. Okay?
What happened if it divergence?
What?
What happened if the derivative diverges? So like the square root.
What happens if you want to write a derivative that diverges? So you want to write a discontinuous function of Grassmann variables.
Well, maybe. I'm asking what is the integral of d eta square root of eta. Is the
Square root
converges?
of eta.
The integral does not converge?
I don't think there's
Yeah.
even a meaning on the
Yeah.
square root.
Yeah, you need to define, I think, a square root because it's the opposite to a square, and square is 0. So yeah, you know the square root is
One
already
over zero,
infinity.
yeah.
It's already infinity because it should be the inverse of the square.
The inverse is not defined.
Inverse is not defined, or at least from a naive perspective, it's infinite.
Infinity.
Yeah, so it doesn't. So then, oh, that was stupid of me. I shouldn't have done that. I could have used this. I'm gonna write it again now, but let me see. Okay. Then commutation 3. In order for our theory to be consistent, we need also if we have psi j eta I, this thing should also be 0, where this is the operator, the fermionic operator, and this is the Grossman variable. So they also anti-commute. And then 4 is Gaussian integral. Oh, you know what? I forgot something. There's something I forgot that I need to go over in a moment. I forgot something here that let me just quickly mention. Bosonic Gaussian integral. Sorry, I forgot this. You know, if I write an integral d phi dagger phi, okay, and I have here e to the phi dagger times some matrix A phi. Okay, A is a matrix now. So do you know how to perform such an integral?
Yeah, it's 1 over the German.
Good. So the point is that what we do is we diagonalize A, then we get eigenvalues. We get a new basis. Now because we use a unitary transformation, okay, or at least orthogonal transformation essentially, then the measure is not changed, okay, and we get just a product of all these Gaussian integrals, which is just a product of these eigenvalues, and we get 1 over the product of these eigenvalues, right? Because each, okay, maybe I'll write that. So we get something like d, let's call it phi tilde dagger phi tilde. These phi tildes are the rotated basis, and then we have e to the, say, sum over j epsilon j phi tilde squared, like this, okay? And then this thing gives us the product over all these j's of 1 over epsilon j, okay? And there's also a factor of pi, but remember that the factor of pi for each one of them is already in this measure thing. And then this gives 1 over the determinant of A, basically. So that's a well-known result. Okay? Now what is going to happen for the Gaussian integral in this case? Then we have an integral, say, d eta var eta, where these are now vectors. Again, space. Now, the whole point is that this is not the complex conjugate of eta. Basically, some other Grassmann variables which are associated with the, so when we perform a permission conjugation in the space of these, in this Hilbert space, then we need, for each eta, we need a corresponding eta bar. That's basically the idea. And then we have something like e to the, say, eta bar a eta. Okay? Now in this case, it's much simpler because we can just expand. So we write the eta bar eta. And then we have something like 1 plus eta bar a eta. And now again we can perform the same. So these Grassmann variables, they also allow us to make transformations, linear transformations, completely fine. So you perform a linear transformation and you get something like an integral d, say, let's call it tilde bar eta tilde times 1 plus sum over j epsilon j eta tilde bar eta tilde. Okay? By the way, this identity here is again the same as before. You see all these higher orders when I expand just vanish. Okay? And then this guy gives me the sum over j epsilon j because this term is 0 because of the rules. And this just gives me det of a. So we see a property that distinguishes fermionic, this is like fermionic, Gaussian integrals from bosonic Gaussian integrals is that in bosonic ones we get 1 over det A, for fermions we get det A. And let's see if I have anything left to discuss. Oh, and then the last thing is the coherent states themselves. So we create them in the following way. We have e to the minus eta c dagger acting on 0, which is equal to 1 minus eta c dagger 0. Okay? And this thing is 0 minus eta 1. And we claim that this is a state which gives us eta times the same state. And let's see how that works. Because if I act with C so this is the state, sorry, this is the state eta. What I mean is that this is the state eta. And if I act with C, sorry, not C, psi. Oh, sorry, psi. Sorry about that. Okay, so psi is some fermionic operator which we described here. Okay, set. I might substitute sometimes eta, psi, C. So please correct me if I do so. So if I act with psi on this, we expect it to give eta times psi. So I'm working exactly on this. So I have psi acting on 0 minus psi eta 1. Okay? Now this thing, it destroys the vacuum state. So this guy is 0. Here we need to interchange them before we can act on the state. So this gives me eta psi 1 because of the anti-commutation between them. And then I get eta times 0. Okay? On the other hand, if I look at eta times eta, okay, that's like eta 0 minus eta squared 1. But eta squared is 0, so that's eta 0. So I see that indeed it gives me eta times 0. And then finally, maybe the last comment is that eta, like this, that's what I was trying to say before. I'm going to interpret it as 0 e to the minus c eta, psi eta bar. Okay, that's how I'm going to interpret it. I hope I didn't get anything wrong. This is like 0 e to the eta psi. Now, what we're going to do is we're going to use all this formalism to derive the path integral from any body state. But before that, let's take a break. Why did we? What? Yes.
The last.
It's wrong. The minus should be here.
No, I just don't understand.
Okay, let's see. So let's try and do this. So let's open this guy. So 0 e to the minus psi at the bar is equal to 0 times 1 minus psi at the bar. Okay. That is equal to 0 minus 1 at the bottom. Okay, now let's act on that with psi dagger. So we want, what we demand is that psi dagger eta will be equal to eta at the bottom. That's what we want. That's how we define it. Okay. So on one hand, if I act, I write 0 minus 1 at the bar times psi dagger. Well, this guy, I want to remind you that it destroys this vacuum because it's the Hermitian conjugate of the other. And here, it's going to give us 0. So we get, so this thing is equal to 1 psi dagger at the bar because we interchange between them and they anti-commute. And then this guy gives 0 at the bar. And if I multiply this whole thing by at the bar from the left, I'm going to get the same.
Eta bar is a real number, just like psi stuff.
I don't think it's a real number. Because, for example, if you take, say, eta bar eta, and you multiply it by eta, what do you get?
0.
Wait,
What?
is it because if you define Grassmann variables, is it a field or a ring or? I mean,
A ring. You're asking in which space it lives?
yes.
No, that's up to you. You
Okay.
can put Grassmann variables on a ring, you can put them in a cluster, you can put them in 3D, you can do with them whatever you want.
So defining the imaginary numbers for the Grassmann variable.
There are no imaginary numbers.
Yeah.
No. This, again, what I was saying is that for each eta, we associate a second eta bar,
Right.
which is linked to it. And that will be, when we perform the Hermitian conjugation operation, they will be linked with each other.
They are linked in a way they are not built to live.
They are independent. the same way that phi and phi star are independent variables. Like you could use x and y as a coordinate basis, or phi and phi star as a coordinate basis. In the same way, they're independent, but we link them in a way that we need. You know, when we describe our Hilbert space, we need to decide. You know, when I wrote this, I needed it to be associated with eta bar. So I need. So in that sense, I create some sort of artificial link to formulate my Hilbert space. But the point is that if I perform complex conjugation is not something I can apply. The whole package of definition conjugation is what takes psi bar. I just do it to have a consistent Hilbert space description. If you like, these Grassmann variables are objects which are my utility. I use them. So I use them in that manner such that I have a consistent theory. Okay? Now, but hey guys, you're supposed to know all this. You already learned it. Okay, so now the point is that all this formalism was in order to define a field integral to compute the quantum partition function. So the quantum partition function the quantum partition function, by the way, you can think about it as something we will use to compute quantities of, say, fermionic and bosonic systems at thermal equilibrium. But you can also relate it to just a general path integral. You'll see in a moment. In this multidimensional space, through what we call a Wick rotation. So, but you know, in the quantum case, this is e to the minus beta h. Okay, and because we might want to use systems that have a conserved number of particles and systems that don't. Like, for example, we saw in the condensed matter theory, condensed matter course, that phonons are not conserved, but we might think of bosonic particles like helium atoms in superfluid or something. Then we could also add to this chemical potential to fix the number. But for now, I'm not getting into that detail. Then we already defined this guy, right? Oh, shoot, I forgot something. One last thing. A trace with a Grassmann variable. To define the trace, we want to do like before. We had the trace of some operator, O, of say psi dagger and psi. Okay, and I want to compute its trace. So as we said before, we can have a sum over n O of psi dagger and psi. And as before, I'm assuming that this guy is normal ordered. Okay, it's normal ordered, and it comes with fermions. This is very important. It comes with the same amount of psi's as psi daggers. Okay, I don't want to look at operators, at traces of operators that are fermionic by themselves, meaning that they have an odd number of fermionic fields. Okay, and so then I can insert a resolution of identity, which I also didn't describe. What is wrong with it? Okay, so I need to yeah, this is all mixed up. So sorry, I need also a resolution of identity. Resolution of identity. So to that end, sorry, I'm all mixed up. I jumped ahead too fast. So I had the Gaussian integral over there. Now let's compute the overlap, say, between eta and I don't know, kappa, I don't know, whatever. Okay. Then this guy is like writing 0 plus eta, sorry, 1 times eta bar. This whole thing multiplies 0 plus, say, kappa 1. Okay, and this thing is equal to 1 plus eta bar kappa, which is, to the best of our knowledge, eta bar kappa. Okay, so that means that we can define a resolution of identity. So again, we have an overlap which looks exactly like before. Okay, so we can define this as a sum over, say, d eta bar eta e to the minus eta bar eta 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 as before. The only difference is that this guy over here is a product over all, say, etas, d eta bar j d eta. Now we're getting some air finally, and there is no pi. Okay, we don't need a pi because the Gaussian integral doesn't have that pi thing, and that gives us is aided by this result. And this means that we can write this guy as a sum over n, and here we're going to stick resolution of identity. Resolution of identity. So we have O, sorry, this is O of psi dagger and psi, and here we have a sum d eta bar d eta e to the minus eta bar eta 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 n. Okay. Now, because we have 2 of everything, we can actually interchange between O and this eta. So this thing becomes sum over n eta d eta bar d eta e to the minus eta bar eta O of eta bar and eta, which is now written as a function of Grassmann variables instead of Oh, no, 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 no. Very bad, very bad. No, no. I jumped. So now, what I want to do is I want to take. Sorry. Okay, let me write this properly. So now I exchange between the integral and so I take this integral outside, and I can do that because this whole thing is quadratic in these guys. So for any minus sign, I collect two such minus signs. And then I have a sum over n O of psi dagger psi eta n. Okay? So let me erase this guy for a moment. We'll do it later. So now what I want to do is I want to take this guy all the way to the other side such that I have an identity. But when I do that, I actually need to interchange this eta with that eta. So what I want to argue is that eta n, sorry, I want to argue that n eta, sorry, what did I write over there? Yeah, sorry, O psi dagger psi n, sorry, eta n is equal to minus eta n O, this is an operator of psi dagger psi n. Okay? And to prove that, first of all, we must assume that this is quadratic in the psi's. So this doesn't participate in this exchange process. The only guy that gives the minus sign is the fact that here we have one Grassmann guy, and here we have another Grassmann. Okay? And maybe a good way of thinking about it, you know, okay, does anybody have any complaints about that or questions? Do you want me to show it?
How did we get the minus?
Okay. So someone does. So we can think about maybe a good way is to look at this and then to look at this. Okay? Let's look at these two. So this guy I'm writing explicitly. This is 0. Yeah. Oh no, I can't do it like this. I need to have some operator. Sorry, I need to have eta, some operator eta. Okay, and and some. Yeah, I'll have to show it. So let's say I have something like this, and I have. Okay, let's try and show it. So I have n eta O psi dagger psi. So allow me instead of this psi dagger psi, allow me to have psi dagger psi as a representative of a general operator which is quadratic. Let's look at this specific case, and here we have n. Okay, and then on the other hand, I want to exchange them. I want to have n psi dagger psi eta n. Okay? And then n can either be 1 or 0. Okay, so let's compute this guy. So this guy looks like, so I have two cases. I have 0 times 0 plus eta 1, okay, times, okay, so this guy just gives me, this guy gives me 1, and this guy gives me 0, so I get 0, okay, so if n is equal to 0, I get 0, because this guy will act on 0 and it's just 0. If I have 1 on the other hand, this guy gives me 1, okay, and then I get 1 between eta and 1 between eta, so I get eta bar. So okay, so let me write that explicitly. This guy gives me eta, and this guy is going to give me eta bar. Okay, so this is if n is equal to 1. Now let's do this guy. So this guy now gives me something else. So this one only chooses the so this guy, so I have, so if n is equal to 0, I have 0 psi dagger psi times eta. What does this guy, okay, let me make some more room here.
That's 0 as well.
That's 0 as well.
Yeah, you can act on the left. So psi dagger.
Psi dagger. That's 0. Okay. So here I get 0 again. Good. Okay. That makes sense. Okay. That's good. Science, math works. Okay. And now the case where it's 1. So 1, I'm going to get 1. Oh, what am I talking about? Oh, Jesus Christ. No. This is not, we want eta psi dagger psi and eta. Sorry. And now this is obvious, right? Because this guy again will choose, okay, this will nullify the 0. But here we get, we trivially get eta bar eta, right? If n is equal to 1. So which is equal to minus eta bar. Okay? So there's a minus sign with respect to them. And you can account for this minus sign by just plugging in minus eta. Okay? So to conclude, what we're going to have is that this guy is equal to d eta bar d eta eta O of psi dagger psi sum over n eta. And this guy, sorry, is just identity. And now when we act with eta on both sides, now because this guy is normal ordered, I can transfer it to become an integral d eta bar, d eta of the expectation value. So I get e to the minus eta bar eta times O what am I doing right now? Sorry, I forgot that there's a factor here of e eta bar eta. But the point is now I have eta bar Okay, so that's how we write the trace for fermions. Just like oh my god, what is going on? No, this becomes minus eta. Sorry, this is minus, right? So here we have minus eta bar O of psi dagger psi eta. Yeah, that's what I wanted to say, right? Is that okay?
Yeah.
Yeah.
Jesus, so many mistakes. Let me see. Good. So yeah, so this in principle we can interpret as an integral d eta bar d eta e to the minus eta bar eta, and then O of minus eta bar eta. That's the trace. Okay. So now we can finally do the path integral. Coherent state. So what we're going to compute is, as I mentioned, the partition function is just the trace of e to the minus beta h. And h can either be a Hamiltonian of fermions or bosons. And then this thing is a sum over n e to the minus beta h n, but we just saw that we can rewrite this guy as an integral d psi bar psi. Now psi is like, you know, phi for the psi is like phi for bosons and eta for fermions. Okay, and then this measure is the associated measure, and then we have zeta psi. Sorry, e to the minus psi bar psi, which is, you know, for the bosons, the bar would be complex conjugation. Zeta psi e to the minus beta h psi. Okay. Now we have a problem, because while we talked about traces for normal ordered operators. Is this operator normal ordered? No. Why isn't it normal ordered? Because even if the Hamiltonian is normal ordered, you know, if I take it to the power n, it's not normal ordered. Obviously. So we need to solve that in some way. And what we do is we write the following thing. Right, because e to the minus beta h is not normal ordered, we can't take its expectation value. So what we do is we write e to the minus beta h bar is equal to e to the minus delta h, not h bar, to the power of n where n is beta over delta. And by the way, this beta, if I didn't mention, beta is 1 over T, the temperature, for now. Okay? And what we've done here is I want to think about these deltas as small increments, very small increments. And then again, we have the same problem. We didn't lose the problem, but the point is that the then if delta is small enough, the corrections to the normal ordered case are negligible. So what do I mean by that? I mean that e to the minus delta h, if I take the expectation value of, say, psi 1, psi 2, okay, then this thing is going to be e to the minus delta h of eta 1 bar eta 2, okay, plus O of delta squared. Okay, and we're going to take, in the end, we're going to take delta to 0. Good. So now, let me write. Now I have that this partition function is equal to an integral d psi bar psi. And I want you to remember that these can be vectors. Okay? They can be, there can be a spatial sum here. This could be like a vector product between two fields where the components are like space, orbit, spin, whatever you want. Okay, so I have your e to the minus psi bar psi, and I have zeta psi, and then I have e to the minus delta h, e to the minus delta h, e to the minus delta h, you get the message, e to the minus delta h psi. Okay? And that's like n time. Now I'm going to stick a resolution of identity here, 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 and here. Okay? So if there are n of these guys, then there are n minus 1 resolutions of identity. So then I have an integral. Now allow me to call this guy, let me denote it by n, like large n. Yeah, you have a question?
Where did rho come from?
This is not a rho, this is zeta. Oh, I forgot to mention, good point. Zeta is 1 for bosons and minus 1 for fermions. This is what I tried to explain before, that when you exchange, you want to get rid of this guy here in the middle. So we saw that it led to this minus 1. See? Okay. Now what I'm going to do, I'm going to write something like j is equal to 1 to n d psi j bar psi j. Okay, and the n guy is this guy, is this psi. So then I have e to the minus sum j equal 1. Oh, sorry. No. then I have psi bar n psi n. I don't know if this is going to work, but I'm tired of looking at my notes, so I'm going to derive it. Let's just go along. And then I have, you know, zeta psi n. Let me call this psi 0. Psi 0, and I write here psi 0 is equal to zeta psi n. Okay, that's my condition. So this is psi 0, e to the minus delta h, psi 1. Sorry, take it back. Each resolution of identity comes with a factor. So I do have a sum over j equal 1 to n of psi bar j psi j. Okay, and each one of these j's can be a vector of spatial coordinates. So it's an inner product, you know, it could be like an integral over space, but everything is implicit. Now, e to the minus delta h, psi 2, psi 2, and then my last guy is like psi n minus 1, psi n minus 1, Jesus. So I'm going to continue here. Then I have psi n minus 1, psi n minus 1, e to the minus delta h, psi n. That's it. Okay. Now, what now? What now? So now I can use this approximation, assuming that I take n to infinity. Then this delta is very small, and I can just substitute all these with their expectation value. Oh, by the way, this is wrong. Why didn't you stop me? Because this is wrong, right? There's something missing. Again, if I write eta 1 e to the minus delta h of psi bar and psi, okay, eta 2 divided by eta 1, eta 2, right? Then it gives what I said. Then it gives e to the minus delta h of eta bar 1, eta 2, plus O of delta squared. Because this is an over-complete base, I can't just take this expectation value. Okay? So what will happen here is that I also have these factors. And then I will use the fact that eta 1, eta 2, okay, this guy is e to the eta bar 1, eta 2. Okay? So now I can multiply all these things. So I get that this is equal to the integral over pi j is equal to 1 to n d psi j bar psi j. A psi of 0 is equal to zeta psi n. Okay, that's our condition. Then we have e to the minus sum over j equal 1 to n. And then I have psi bar j psi j minus psi bar j. So you see this is always, it's psi j plus 1. Okay, this is all of these guys. And then I have minus delta H of psi bar J psi J plus 1. Is that okay? Any
Why do you have
complaints?
the JJ?
Why do I have the JJ term?
Yeah.
The JJ term came from the fact that this is the resolution of identity. Oh, by the way, this is a plus. Okay, so each, I inserted here a resolution of identity. The resolution of identity is not written on the board, but it comes with this factor. Okay, so that's one thing. Then this part, this term comes from the overlaps, because we said that these are over complete, so they're not orthogonal to each other, or they're not normalized. Okay, and then this guy is that guy. Okay, and I closed the parentheses. And the plus is because I took a minus out.
Right. Yeah. Okay.
Git. So now the last step is to rewrite this as a derivative. So I'm writing it here. I have an integral psi 0 equals zeta psi n. Pi j is equal to 1 to n d psi j bar. And now I'm going to write it as e to the minus. So I have some j equal 1 to n. And I'm going to put here a delta. Delta. I'm going to open a parenthesis here. And then I have psi j bar times psi j minus psi j plus 1 divided by delta. Okay? And plus h of psi bar and psi j j plus 1. Okay, now we identify this guy in the limit where we take n to 0. We identify this guy as a integral, right? And this guy as a derivative.
N to infinity, right?
N to infinity. And this guy will become a measure, basically. So we can write this thing as an integral where psi of 0 is equal to zeta psi of beta, okay, d psi bar psi, okay, e to the, oh, we have a minus here, right? E to the minus s psi bar and psi, and this s is not other than the action in Euclidean space, which gives us an integral from 0 to beta d tau. This is this integral, and then we have minus psi bar d tau psi, right? This is minus the derivative of psi plus h psi bar psi. Okay, and the only condition we have, which we will see later how it affects us, is that there is some sort of periodicity. Okay, this path integral, if you like, is a path integral over configurations of these fields. So we have, remember that this psi and psi bar are associated with, say, A and A dagger, respectively. Okay, and we're talking about coherent states. So we're integrating over coherent states, and we're asking what is the probability to start in some some coherent state. Where is it here? We're asking what's the probability to start in some coherent state and to end in some coherent state, or to start in some coherent state and end in the minus of that coherent state, depending on whether it's bosons or fermions. And what else? Another thing is that you can view this action as a Euclidean wait, is this actually, wait a second. Yeah, so if I would do a real time integral, right? I should have e to the I over h bar s of psi bar and psi. That's in real time. Okay, where this s, where s would be an integral over dt, which I'm not specifying what it is. And then I'm going to have I, sorry, not I. How does it go? Oh, maybe, yeah, maybe I do. Maybe I have here psi bar minus I dt psi minus h of psi bar and psi. And we see that if we take tau, if we take t is equal to I tau, right? Minus I tau. Minus I tau. Then I think we get exactly the result we had there. I tau or minus I tau. Maybe it should be I. Never mind. I. So what I'm trying to say here. Wait, is it actually? Yeah, I guess. Okay, I'll get back to you about this. But what I'm trying to say is that another way you could view this integral is not a thermal average, but just a weak rotation of a path integral in real space. Okay? Although then we need to describe exactly what we're calculating. Okay, but it definitely gives us a way to compute systems close to thermal equilibrium. Second thing I want to mention is that you see that we have this emergent coordinate which we call tau. Tau is known as imaginary time and it has no meaning. Okay, no, seriously, it has meaning, but it's not, you can interpret it as a weak rotation of real time. But besides that, it's more of a mathematical trick which helps us to calculate thermal averages. Now, what is this time? This time is the price that we pay, okay? Because we want to compute a quantum average, yeah? But we don't want to use operators. So something needs to keep track of the fact that operators don't commute with each other, which we lost when we went to numbers. Now it's true that the Grassmann variables know about the anti-commutation relation between different operators, but they don't know about the non-trivial commutation relation between the same, like C and C dagger of the same state. And this is exactly encompassed in this term. So one way to view this time dependence is that any, these fields, they can fluctuate in space, because remember that this is like a vector product over different, spatial coordinates or orbital coordinates and so on. And the, space fluctuations is what we're used to from classical statistical mechanics, for example. But they can also fluctuate in this time, this tau. And these fluctuations in time is what we call quantum fluctuations. Okay? So why am I saying that? Because imagine that I were to assume that these fields, psi and psi bar, do not depend on time. Then this time derivative would fall. This integral would become trivial, would just give beta, and I would have e to the minus beta h of these classical fields. And that's exactly the limit where I get a classical statistical mechanics, just the free energy. Okay, it's just the usual Gibbs free energy, and that's it. What else do I want to say? Yeah, and the last thing is that, you see, when you identify this structure, I want you to be aware of this kind of structure, because what this tells us, remember that this is some field, which it's like a coherent state associated with a dagger, and this is associated with A. So the fact that they multiply each other in the field theory and have this single time derivative is exactly what implements the fact that they don't commute with each other so easily. So anytime you see like some operator, time derivative, times another operator, you know that in the Hamiltonian version of this Lagrangian, these guys shouldn't commute. And it makes sense, because if I take a time derivative of one of these things, then I'm going to get a Hamiltonian, basically some sort of a Hamiltonian equation, or like a diffusion equation. Okay, so that's all I wanted to comment about that. How am I with time? I don't have much time, but let me maybe finish by describing these Matsubara frequencies. So technically, what we do often when we try to compute path integrals of this type is we use Matsubara frequencies.
So another way of seeing it is you gain a dimension, right?
Ah, yes. This is another thing that I would like to mention, is that that's true. That what we see in the end is that our theory, so say we had some space, and now we have this coordinate tau, which goes from 0 to beta, and then there is either periodic or anti-periodic boundary conditions on this cylinder. So basically the object on which we are integrating now looks like this kind of generalized cylinder. Okay, and when we take beta to infinity, it's like taking the cylinder to infinity. And then we have Fourier transforms and stuff like that, which we'll discuss in a moment. But what did I want to say about that? I wanted to say something, but I don't remember what. Yeah, we got an extra dimension. Oh, I know what I wanted to say. So in many cases, one of the interesting facts is that in many cases, you'll find that these okay, due to this mapping, there are many situations in which you can write, basically it's all the bosonic theories. All the bosonic theories that are inherently bosonic, you can rewrite them. Oh, up to gauge fields. One needs to be careful with the gauge fields. I'm not getting into gauge fields. Okay, let's put that aside. But if you have a bosonic theory which is not gauged, It basically means that at dimensions, like if you have a d-dimensional problem of a bosonic theory, which is not gauged, then it's actually equivalent to a classical statistical mechanics field theory in d plus 1d. D plus 1 dimension. Okay? And the extra dimension is this now. Okay? So that's a very powerful statement. It means that basically everything we know about statistical mechanical models, we can use it to understand quantum models. Okay? But what makes it more interesting is that, you know, fermions, for example, do not have a classical counterpart. So there, with gauge fields, also you can have situations where the action is actually complex, and you can have all sorts of interesting stuff where this guy here is not exactly a well-defined probability. It can oscillate, it can be complex, and stuff like that. And that's the interesting situations. Okay? That's Matsubara frequencies. Okay, so now, as I mentioned, you know, we want to take advantage of Fourier theory, as we know it diagonalizes. We've seen already, right, that you know, the way we solved most of our models is we took a Lagrangian, we got a Hamiltonian, then we Fourier transformed the Hamiltonian, and then we used A and A dagger to diagonalize. Now what we see is basically we take these Hamiltonians and we write them in terms of a path integral, but we notice that we develop another derivative. We develop another dimension and another derivative. So in order to also, you know, diagonalize that part, we need to also perform a Fourier transform with respect to this tau. So we define psi of tau as equals a sum over omega n, e to the minus omega n, psi n, and therefore psi n is 1 over beta, the integral from 0 to beta d tau e to the I omega n tau omega of tau. Now, these are states on a cylinder. So, for bosons, we know what this omega n need to be, right? They're just 2 pi n over beta. If bosons, in case of bosons, and then it's periodic. But if we have an anti-periodic condition, then we need to write 2 pi n plus 1/2 over beta for fermions. Okay? And n is basically in Z. This is something I always kind of bugged me. I never really worked it out. Because in principle, if you have oh, no, that's fine. Okay, so one thing to notice is that, now I worked it out. So because the integral is between 0 and beta, you could think about an equivalent integral between minus beta over 2 to beta over 2. And then, you know, you need to sum over negative and positive components. Let's see. And now let's look at some typical Hamiltonians. So let's say let's just look at an example. So say our Hamiltonian was a sum over d3p over 2 pi cubed h bar omega p a dagger p a p plus integral d3q d3k over 2 pi 6 uq a dagger a p plus q k minus q k p. Okay. Then our action, the action that we get S is going to be sum over omega n and integral d3p over 2 pi cubed. And then I open this guy up, so I'm going to get where is the time derivative? You see I have d tau on psi, that gives me minus I omega. With the minus here I get I omega n. And then I have plus h bar omega p. Phi star n of p, phi n of p. And then this guy here is going to be equal to, okay, so here we need to be careful because I want to remind you that this whole thing was local in time. So when I do the Fourier transform local in time, then I get this mess that you're going to see right now. I'm going to have, you know, like n prime and I don't know, nu, whatever. And then I'm going to have an integral d3k d3q divided by 2 pi to the 6. Then I have this uq, stays uq, but then I have something like phi star, say n plus nu p plus q, phi star n prime minus nu k minus q, phi of n prime and k, phi of n and p. How's that? Okay, that would be a typical theory. This would be the quadratic part of the theory. This is what we call d naught to the minus 1 of I omega n and p. That's the inverse Green's function.
And there's a 1 over beta, right?
The 1 over beta here.
In the second.
Oh, right. Yes, yes, of course. Beta.
Good.
And here there is something. I don't know if there's a beta in front. Let me see. I think there's a beta here in front of this whole thing. Let's see.
There's 1 in the first one, and there 2 in the second one.
Let's see. So let's assume that we substitute this, and then we perform the integral. The integral gives a beta. Yeah, each integral gives a beta. So maybe it's just beta over the times the whole thing, right?
Right.
Yeah. So it's like this, I think. Because you see, this sum doesn't have any units. So this object has the same units as that.
Right.
Okay? So I think this is might be a good place to stop. What's the time right now? Or is it too early? I think it's a good place to stop. So next class, so now we have the path integral. Next class, what we're going to do is we're going to get used to performing like computing stuff with these Matsubara frequencies, and then I'll also show what you asked about the relationship between the propagator and the Green's function. And then we'll have a tool. We'll have a way to compute many-body path integrals or understand what they mean. And then we'll move on to do to the basically the second part of the course, which is not, which is actually utilizing quantum field theory to compute stuff like maybe we'll do like instabilities, perturbation theory, renormalization group, dealing with disordered systems, stuff like that. Okay, but we still have something to finish. So, but we're going for a break right now, right? Because we're going for past. We were not meeting next Thursday, right?
Right. Yeah.
So have a happy Passover.
Thank you.
Thanks.